what we've done is so far, and don't write this down, we have solved quadratics. Alpha of x is equal to ax squared plus bx plus c. And we solve by factoring, or we solve using the quadratic formula. When we got to something like ax cubed plus bx squared plus cx plus d equals 0, what I did where we were looking for the zeros and determining whether they crossed or bounced by seeing if there was an odd or even number, I gave you a situation where you could solve this cubic by factoring by grouping. Factor something out of the left pair and factor something out of the right pair, and you ended up with a common factor. So we made up some special problems that would work that way. Well, not all cubics will work out so that you can factor by grouping, and then we're going to get to fourth power, fifth power, and we could go obviously to an infinite power, which wouldn't be very fun to solve. But we do need to know how to find the roots, and to find the roots, what we're going to do is we're going to use synthetic division to find the roots. And you know you have a root when you get a remainder of 0. It divided evenly, see? Because a root comes from a factor set equal to 0 and solved, right? A root comes from a factor that is set equal to 0 and solved. So if you find a factor, that's something that divides evenly, and we can find out if it divides evenly by doing synthetic division and getting a remainder of 0. Well, if we don't know anything to divide by, remember in our synthetic division we had a factor to divide by? And so we would take this problem and we would, don't write this down either, we would put 1, 1, -4, -4, and then we would put our root right there, and then we would start the process of bringing down. The problem is we don't have anything to put there because it didn't tell us what to divide by. So you could just randomly start picking numbers, but there's an infinite set of things you could put there. +1 -1, +2 -2, +3 -3, +1,000 -1,000, +1/10 -1/10. So you could check all day. If you do synthetic division and you get a remainder of 0, then you know you found a root. And the root is going to be that number. The factor would be x minus that number, right? But we don't have a number to put in there. The rational root theorem is a theorem that allows us to find all the possible roots. Instead of having an infinite number of answers, or an infinite number of choices to plug in here, we're going to get down to 5 or 6, 8, 10, 20. That's better than an infinite, okay? So that's the purpose of the rational root theorem. Well, here's how the rational root theorem works. The leading coefficient is 1, and we would look at that last coefficient, -4. That's the constant. So we have the leading coefficient, and then we have the constant. So what we're going to do is take plus or minus, and you can start writing this down, plus, minus, all of the factors of the constant each over all of the factors of the leading coefficient. Now, we're only going to write that down once. I just wanted to write it down once so you could have in words what we're doing. We're going to take plus or minus all of the factors of the constant each over all of the factors of the leading coefficient. Now, It may be that I need to color code this, plus or minus all of the factors of the constant over all of the factors of the leading coefficient. I'm going to let you write that down, and then we'll start through this process, okay? Now, what are all the factors of 4? 1 times 4 and 2 times 2, right? What are all the factors of 1? Just 1. So we're going to take plus or minus all of the factors of the constant. Everybody with me? Over each of the factors of the leading coefficient. Now, if that was a 2 in front of that x cubed, we'd say plus or minus 1 over 2. 1 or 2. If this was a 2 instead of a 1, then the factors would be 1 and 2. So we'd say plus or minus 2 over 1 or 2. We'll look at that in a minute, okay? Now, then here's our combinations. If we take this situation right here, we're going to do plus 1 over 1, minus 1 over 1. But if it's a whole number, we're going to turn it into a whole number, okay? So we're going to have positive 1 over 1, which is positive 1. Negative 1 over 1, which is negative 1. Positive 2 over 1, which is positive 2. Negative 2 over 1, which is negative 2. Positive 4 over 1, which is positive 4. Negative 4 over 1, which is negative 4. Least to greatest, if you wanted to, that would be negative 4, negative 2, negative 1, 0, 1, 2, not a 0, sorry, negative 1, 1, 2, 4. If we're going to write them as a solution set, we need to put them least to greatest. So if we were going to just start randomly trying to find a factor to put in that little box to do synthetic division, we wouldn't choose from an infinite set anymore. We have 6 to choose from. That's better than infinite, you see. You're going to see this working in a minute. Everybody see the rational root there? That means that these are the possible rational zeros. Now, did you hear what I said? The possible what? Rational zeros. That means there could be some zeros with a square root in it. Or there could be some zeros with an imaginary root, right? This isn't those possibilities. It's only the rational possibilities. Okay? So there's 6 possible rational roots, and then there's the possibility of a bunch of goofy looking radical and imaginary roots. All right. They say we got that. Okay, so number 2. We want all the possible rational roots. This is a quartic. It's 4th power. So what we're going to do is what? We're going to take the factors of the constant. I'll keep it in blue and green just to be color-coded. And that's 1 and 6 and 2 and 3. And then we're going to take the factors of the leading coefficient, and that's a 1 and a 4 and a 2 times 2. So what are we going to do? Plus or minus each of the factors of the constant, each over the possible factors of the leading coefficient, 1 or 2 or 4. 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 Now this one's got a lot of possibilities. You've got plus or minus each of the factors of the constant, each one over each of the factors of the leading coefficient. Now, I'm just going to call this a pod. I don't know why. But anyway, in this pod, how many things are going to pop out of that? 1, 2, 3. But plus or, I knocked off my minus with my bar. But a plus or minus, so it's going to be 6, right? Okay, so we're going to have plus 1 over 1. We're dealing with the 1, right? Plus 1 over 1, which is 1. And then minus 1 over 1, which is minus 1. And then we're going to have plus 1 over 2, which is a half. And then we're going to have minus 1 over 2, which is negative a half. And then we're going to have plus 1 over 4, which is a fourth. And then minus 1 over 4, which is negative a fourth. And we get those 6 things out of that first pod. Okay? Understand that? Then we've got this second pod. So we're going to have plus 2 over 1, which is 2. Minus 2 over 1, which is negative 2. Plus 2 over 2, which is 1. Minus 2 over 2, which is negative 1. Plus 2 over 4, which is 1 half. Minus 2 over 4, which is negative 1 half. That's the second pod. Notice we're getting some doubles. We'll only use them once, but all right. Now we got the third pod. We got positive 3 over 1. That's a 3. Negative 3 over 1 is a negative 3. Positive 3 over 2, which is a 3 over 2. And then negative 3 over 2. And then 3 over 4. And then negative 3 over 4. And that's that pod. You understand what we're doing? And then we've got the fourth pod. We got plus 6 over 1, which is positive 6. Plus, or minus 6 over 1, which is minus 6. We've got plus 6 over 2, which is 3. We got minus 6 over 2, which is negative 3. We got plus 6 over 4, which reduces to 3 over 2. We got minus 6 over 4, which reduces to minus 3 over 2. Now, we're going to put them least to greatest because we want them as a solution set. The very least was negative 6. And there's not another one. The next least is negative 3. And there's another one there. So we'll only take it once. The next least is negative 3 over 2, which was negative 1.5 actually. So, oh, was there a negative 2? Missed it. Thank you. Yes, there's a negative 2. And then the negative 3 over 2. So we got rid of the negative 3 over 2's and the negative 2. And the negative 3 over 2 is a negative 1.5, right? And then the negative 1 would be next. And then the negative 3 over 4 would be next. Oh, there's another negative 1 here we need to get rid of. Negative 3 over 4. Negative 1 half. Negative 1/4. This is good lining up fractions least to greatest. Next is positive 1/4, right? Positive 1 half. Positive 1. I left 3/4 out. Positive 3/4. Like to miss my 3/4. positive 1, three over 2. I'm going to run out of board. After positive 1/4 is positive 1/2. And after positive 1/2 is positive 3/4. And after positive 3/4 is positive 3 over 2. And after positive 3 over 2 is positive 1. And then positive 2. No. I'm sorry. It was positive 1. And then positive 3 over 2. And then after that we have a positive 2, a positive 3, and a positive 6. So we've got, starting here, negative 6, negative 3, negative 2, negative 3 over 2, negative 1, negative 3/4, negative 1/2, negative 1/4, positive 1/4, positive 1/2, positive 3/4, positive 1, positive 3 over 2, positive 2, positive 3, positive 6, and then we could close our little bracket. Sorry we wrapped around. Everybody understand how we found all the possible real rational roots? Okay? Okay? But that's better than an infinite number of choices. Okay? Okay, well, what are we going to do with that? Well, we want to find the roots of this. How many are there going to be? How many roots are there going to be? Well, it's a third degree polynomial, so there's going to be 3 roots. And we don't know any. So we can't start dividing to reduce it to a quadratic because we don't know what to divide it by. So we have an infinite number of choices until we apply the rational root theorem and we get down to a handful of choices, and then we just start. Okay, so A, we're going to list all the possible rational roots, okay? And so we're going to take the factors 1, 2, 3, 6, and the factors 1, 2, and we're going to find all the possible rational roots. So we're going to have plus or minus 1, plus or minus 2. I better give myself some space, hadn't I? Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, over 1 or 2. And I was going to do that in green. Doesn't matter, but oh, try to stay color coded here. Okay? No, it's the factors of the coefficient. The factors are 2. So we have the factors. We have the factors of the constant 6 on top. We have the factors of the leading coefficient on bottom. Okay? Now, that turns into 1 over 1, which is 1, negative 1 over 1, which is negative 1, 1 over 2, which is a half, negative 1 over 2, negative a half. That's the first set. 2 over 1, which is 2, negative 2 over 1, which is negative 2, 2 over 2, which is 1, negative 2 over 2, which is negative 1. There's the second set. 3 over 1, which is 3. Negative 3 over 1 is negative 3. 3 over 2, negative 3 over 2. That's the second set. Third set. Fourth set, 6 over 1. Negative 6 over 1. 6 over 2. And then negative 6 over 2. So then we'll arrange them from least to greatest. And we would have negative 6, negative 3, negative 2, negative 3 over 2, negative 1, negative 1/2, positive 1/2, positive 1, positive 3 over 2, positive 2, positive 3, positive 6. So we found all of the possible real rational roots using the rational root theorem. That was step A. I'll let you catch up. I know it takes a little bit of time to do that. I went through that in faster because we just did 2 of them. Now what we have to do is start using trial and error to do synthetic division on those until we get a hit. You may get it on the first one. You may get it on the 6th one. It could take some paper to get this done if you miss a few times. Okay? Now, how do you know you got a hit? When you get a remainder of 0 with your synthetic division, okay? And we'll talk about what that means. Is everybody ready to take off on that? So what we're going to do is we're going to now do the synthetic division. I'm going to clean that up so you can see what we're going to do. Remember, on synthetic division, we take the coefficients only. Make sure that you put zeros if there's something missing. So we would have 2, 3, 2, negative 3, negative 11, and 6. So we're set up. Now, if you run out of room on your homework and stuff, you might want to erase out and start over and erase out and start over instead of using 46 sheets of paper, okay? Now, we probably don't want to start with negative 3 over 2. We might want to start with 1 and negative 1, okay? I mean, you can start with whatever you want, but you might get an idea of this is throwing me way off, so I need a number that looks different than the one I started with. Let's just start with 1. So we're going to try this possible rational root right here. I'm sorry, I'll get it out of the right list. We're going to start with that one, just like it, because it looks like a clean one. Do what? So we're just going to put a 1 there. And then how do we do it? We bring down, and then you multiply and bounce it up, right? So 1 times 2 is 2. And then we add, and then you multiply and bounce it up. Negative 1 times negative 1 is negative 1. And then you add, and then you multiply, and then you add. Did we get a remainder of 0? Nope. But what do we know about that? It didn't help us. It didn't find a root for us, but what do we know about it? We know that there's a point whose x is 1 and whose y is negative 6 because of the remainder theorem, right? So if we were going to try to graph this, we don't just want to totally throw that away. That does give us the information that the function value at 1 is negative 6 in case we needed another point to look at. Okay? So we're going to try something else. So we'll just try the root of negative 1. So we're going to bring down, we're going to multiply, we're going to add, we're going to multiply, we're going to add, we're going to multiply, we're going to add, we got a remainder of 0, so we got a hit. So this is a root. We found all the possible rational roots, and we're trying them randomly to find one that works. Okay? Yes. A positive 6. Rip-roll. I quit looking. So that's not a hit. So it's not a root because that really wasn't a 0. Sorry about that. Okay. So, but what do we know? We have the point -1 and 12 if we needed another point. Okay. And you see that you can keep on and on and on. And so we'll keep trying. Let me find one that works. Okay? I'm just going to skip the one that works. -2 works, so we'll go in the -2. You can see that you're going to have some trial and error going on here. That's the only way to get it done. So we're going to try the possible rational root of -2. +2 didn't work either. Okay? Thank you for the correction. So we have a 2. We multiply -4. Add -7. Multiply 14. Add 3. Multiply -6. Add 0. There's that remainder of 0, so yes, this one really is a root. So -2 is a root. Now, what does that mean? That means that we have x what? +2 times. It was the third power, so what's that one going to be? Second power. Right? Now we're going to set it equal to 0 if we want to find the zeros, right? So what can we do now? We know one of the roots. We know the root that comes from this factor. We need the 2 roots that come from the other part. The other part is a quadratic. Once you have a quadratic, you either factor or use the quadratic formula, right? So at this point, we can use the AC method of factoring or the quadratic formula. Which one do you want to use? AC method. So if we use the AC method, we would multiply the A times the C. 2 times 3 is 6. We focus on the fact that it's positive. What do you do next? Find the factors of 6. If it's positive, they have to be what signs? Same sign. We pick the pair that add to give you the B, which is negative using sign rules. So we say our sign rules when you add or subtract with, same sign U, add and take the common sign, which needs to be negative, so they need to be the same sign and negative, same sign and negative. We said we did the signs. And which pair gives us that -7? -1 and 6. So we're going to split the middle term into those 2 pieces. We change the -7 into -x minus 6x. So we have 2x squared minus x minus 6x plus 3 equals 0. And then we factor the left pair. You can factor out an x. Factor the right pair. You can factor out a -3. You need to take the negative off so it don't end up on the inside. Okay? Understand that? So x times what is 2x squared? X times what is -x? -1. -3 times what is -6x? 2x. Negative 3 times what is positive 3? Negative 1. And we see that common binomial that we wanted. I'm going to move that over here. So now we're going to write that as the product of two binomials. The first binomial is that common binomial that you see, 2x minus 1. And the second binomial are the pieces, x minus 3. Now we set each of those equal to 0. Either 2x minus 1 equal 0, or x minus 3 equal 0. We're going to solve, so we add 1. 2x equal 1. Divide 2, x equal 1/2. Or we would add 3, x equal 3. So the zeros of this quadratic, if we put them in solution set, were the negative 2 least, 1/2 next least, 3 greatest. It was an x to the third power, therefore it has 3 roots. We said we found the roots. It had 3 factors. The factors were x plus 2, and then from the quadratic, 2x minus 1 and x minus 3. Any questions on finding the roots of a polynomial function of a degree higher than 2? Okay? Any questions? All right. Number 4. Number 4, we want to list all of the possible rational roots. The factors of 6 are 1, 2, 3, and 6. That's the factors of the constant. The leading coefficient was 1. All of the factors of 1 are 1. So we're going to have plus or minus each of the factors of the constant, each over all of the possible factors of the leading coefficient, which there's only one choice this time, which makes it easier. Understand that? So we'll write out all those possible factors. So we're going to have positive 1 over 1, which is 1, negative 1 over 1, which is negative 1, positive 2 over 1, which is 2, negative 2 over 1, negative 2, positive 3 over 1, 3, negative 3 over 1, negative 3, positive 6 over 1, 6, negative 6 over 1, negative 6, lined up from least to greatest, negative 6, negative 3, negative 2, negative 1, positive 2, positive 3, positive 6. So those are the possible real rational roots. What do you do after that? Start trial and error with synthetic division until you find one that is really a root, right? And how do you know that one really is a root? You get a remainder of 0 with your synthetic division if you don't make an error in the process. So we would take these coefficients, 1, 4, negative 3, negative 6, 1, 4, negative 3, negative 6, and we would begin doing synthetic division with those possible rational roots until we get one that's a hit. So we'll just start with the 1. So we would bring down and get a 1. would multiply 1 times 1 and get a 1. And then we would add and get a 5. And then we would multiply and get a 5. And then we would add and get a 2. And then we would multiply and get a 2. And then we would add and get a negative 4. And that was not a 0, so we know that that's not a root. But we do know that the ordered pair 1, negative 4 is one of the points on that graph. So then we try another root. Our numbers were 1, 4, negative 3, negative 6. We'll try the root negative 1 this time. So we're going to bring down the 1. We're going to multiply. Negative 1 times 1 is negative 1. We're going to add and get a 3. We're going to multiply negative 1 times 3 and get a negative 3. We're going to add and get a negative 6. We're going to multiply negative 1 times negative 6 and get a positive 6. We're going to add and get a 0. And since we got a remainder of 0, we know that the negative 1 is a root. So, as a factor, it would look like x minus the root negative 1. So as a factor, it actually looks like an x plus 1, right? As a factor, it looks like an x plus 1. The root was the negative 1. It began to the third power. So that number right there drops in power from 3 to 2. So it's an x squared plus x minus 6. When you take the factor of it, do what? Oh, 3x. Oh, I lost my 3. Wow, not good. So 1 reduces in power by 1x squared plus, there's my 3, sorry, x minus 6. So I have that first factor times this what's left, x squared plus 3x minus 6. We need to solve the second part, and we can think, what can I multiply to get negative 6 and add to get a 3, right? Because the a is 1. When a is 1, you can think, what do I multiply to get my c and add to get my b? What can you multiply to get 6 and add to get 3? Nothing. What does that tell you? It doesn't factor. So you have to use the quadratic formula. So my a is 1, my b is 3, my c is negative 6. I'm going to plug them into the quadratic formula, which is x is equal to the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. And so I'm going to have x is equal to the opposite of a positive 3, which is a negative 3, plus or minus the square root of b, which is 3 squared minus 4 times a, which is 1 times c, which is negative 6, all over 2 times my a of 1. So it wouldn't factor, so we had to use the quadratic formula. That tells me that there's possible irrational or imaginary roots on this one. We're going to do the square, the multiplication, and the multiplication here. We're going to get x equal negative 3 plus or minus the square root of 9. 4 times 1 is 4 times 6 is 24. When you multiply, there's 2 negatives on that end, right? When you multiply even number of negatives, the answer is positive. All over 2 times 1 is 2. We can now do the 9 plus 24, which is 33. So we get x equal negative 3 plus or minus the square root of 33 over, all over 2. And so we get x is equal to negative 3 plus square root 33, which will not break down over 2. X equal negative 3 minus square root 33 over 2. And the first one that we had found, x equal negative 1. So those are the 3 roots of the quadratic, of the cubic, excuse me. Which could be written as ordered pairs, the x's that make y 0, right? Any questions on synthetic division and using the rational root theorem to find the roots of a higher ordered polynomial? Okay, we'll stop right there.